Hello students, myself Shrimati Bhosle from MJS College Srigonda, and this is the 7th lecture of Standard 12 Chemistry chapter number 9, Coordination Compounds. And in this lecture we will be covering the topic limitations of VBT. We will be studying crystal field theory, that is CFT, and the factors affecting crystal field splitting parameters, that is delta O. So let's begin first with the limitations of VBT. Now in the previous lecture we had studied about valence bond theory, that is VBT, and we have studied some high spin complex, low spin complex, and square planar complex, as well as tetrahedral complex, and seen their geometry. But this valence bond theory has some limitations, and it cannot be used, or it cannot tell the structure of each and every complex. So let's see what are the limitations. The first limitation is that it does not distinguish between the strong and weak field ligands. So this, using this theory, you cannot identify or tell the difference between the ligands, that is whether the particular ligand is a strong field ligand or a weak field ligand. Second limitation is that it does not explain the high spin or low spin nature of the complex. So it cannot tell you whether a particular complex is high spin or low spin nature. Third point is that it cannot explain the color shown by the coordination complexes. Now we know that the coordination complexes are the colorful complexes, but VBT cannot explain why the color is shown by these coordination complexes. And the last point is that the structures predicted from VBT does not always match with those determined from experiments. So VBT is a theoretical concept, and by using this theory, if you deduce the structure of some complex, and if you same carry out the experiment, it does not match with the structure predicted from the VBT. So therefore crystal field theory was proposed, and it has been widely accepted. Now it is based on some assumptions. So let's see what are those assumptions. The first assumption is that the ligands in this theory are treated as point charges, and the interaction between the metal and ligand is considered purely electrostatic. That is, there is no orbital interactions between the metal and ligand. And the isolated gaseous metal ion in has 5 d orbitals, that is dz square, dx square minus y square, dxy, dyz, and dxz, and these all are considered as degenerate, that is they are having the same energy. But second point is that but when the ligands approach the metal, the degeneracy of the metal ion is lost, and these ligands, they create a crystal field around the metal ion. So now these d5d orbitals, they no more remain degenerate, that is they are not having the same energy. Now when the ligands approach the metal ion, the 5d orbitals are split into two sets. First is T2g and second is EG. Now T2g set has 3 d orbitals, which are dxy, dyz, and dxz orbital, while EG set has 2 d orbitals, that is dz square and dx square minus y square. Now this T2g and EG set, they are separated by an energy difference known as delta O, O for octahedral, and this difference is called as crystal field splitting parameter. Now this delta O, that depends upon the strength of the ligands, and therefore the ligands in this theory are classified as strong field ligands and weak field ligands. Strong field ligands cause more splitting of T2g and EG orbitals, that is the delta O value is more for strong field ligands, and weak field ligands causes less splitting, that is delta O value is less for weak field ligands. So these are the shapes of 5d orbitals, dyz, dxz, and dxy. Now in this 3d orbitals, the lobes of the orbitals are pointing in between the axes. So in dyz, the lobe is pointing in between the y and z axis. In dxz, the lobes are pointing in between the x and z axis, while in dxy, the lobes of the d orbitals are pointing in between the x and y axis. While this dx square minus y square and dz square, these d orbitals have their loops pointing along the axis. So in dx square minus y square, the loops are pointing along the x and y axis, and in dz square, the loops are pointing along the z axis. So now let's see the difference between strong field ligands and weak field ligands. Now the strong field ligands causes large splitting of d orbitals, while the weak field ligands causes smaller splitting of d orbitals. Now these ligands are those which are having donor atoms as carbon, nitrogen and phosphorus. So example is cyanide, carbon monoxide, ammonia. These ligands are strong field ligands, while the weak field ligands are having donor atoms halogens, oxygen and sulfur. So example of these ligands are fluoride, chloride, bromide, iodide, thiocyanide and oxalate. Now in strong field ligands, pairing of electrons take place, while in weak field ligand, pairing of electrons do not take place. And the last point is that strong field ligand form low spin complexes, while weak field ligand form high spin complexes. Now, based on this, the ligands can be arranged in the order of increasing field strength. So, iodide is the weak ligand field, while carbon monoxide is the strongest field ligand. Okay, strong field ligand. So, here iodide, bromide, chloride, sulfide, fluoride, hydroxide, oxalate, water, thiocyanate, EDTA, ammonia, ethylene diamide, cyanide, and carbon monoxide. These ligands are arranged in the increasing field strength. Now let's move to the topic splitting of d orbitals and formation of octahedral complexes. Why this splitting of d orbitals take place and how the formation of octahedral takes place. Now in octahedral field, we know there are 6 ligands which approach the metal ion along the x, y and z axis. Now we have seen that the 3 d orbitals point in between the axis, while 2 d orbitals are having their loops pointing along the axis. So as the ligands approach, the degeneracy of the d orbitals is lost. That is, the 5 d orbitals are no more having same energy. They are distributed in two sets, that is Eg and T2g. Now Eg orbitals are dz square and dx square minus y square, and as we have seen that these d orbitals are having their loops along the axis. So the ligands are coming along the axis. So they will repel these orbitals more, and hence they are having more energy than the T2g. They are raised to higher energy than the T2g orbitals. And the difference between the two is given by delta O or 10 dq units. So this is the diagram of crystal field splitting in octahedral complexes. The 5d orbitals are degenerate when there is no ligand. As the ligand approaches, these are divided in two sets, Eg and T2g. So Eg is raised by an energy of 3 by 5 delta O or 0.6 delta O, while T2g are lowered in energy by 2 by 5 delta O or 0.4 delta O. The difference between these two sets, energy set, is given by delta O or 10 dq. This is the energy separation between the two levels. Now for electronic configurations D1, D2, D3, D8, D9, D10, the high spin and low spin configurations cannot be distinguished. That is, they are same. There is no difference between the high spin and low spin configuration. But for D4, D5, D6 and D7, the high spin and low spin complexes have different electronic configuration. That is, their d orbitals are different. So let's understand in D4. In D4 high spin complexes, the 3 electrons first enter the T2g orbital, and the fourth electron is included in Eg orbital. While in low spin complexes, 3 electrons fill up the T2g orbital, while fourth electron enters the T2g orbital only. That is, the pairing of electrons take place in low spin complexes. In D5, 3 electrons are first entered first entered T2g orbital and the 2 electrons entered the Eg orbital, because in high spin pairing do not take place. While in low spin complexes, 3 electron first enter T2g orbital and the remaining 2 electron also enter the T2g orbital, because in low spin complexes pairing will take place. While in D6 orbital, now again is same, first 3 orbital will enter T2g orbital, next 2 electrons will enter Eg orbital. Now all the orbitals have 1 electron each, so the 6th electron will now paired up with the T2g electron, and in this way the electronic configuration is there for high spin D6 electronic configuration. While in low spin, first 3 electrons will enter T2g orbital and next 3 electrons will also enter T2g orbital, making all the electrons paired in the low spin complexes. In D7, again first 3 electrons will enter T2g, next 2 electrons will enter Eg, and the remaining 2 electrons will paired up with the T2g orbital each. While in low spin complexes, first 3 electron will enter T2g, next 3 will also enter T2g, because in low spin complexes pairing takes place first and the remaining 7th electron will enter in Eg orbital. So in high spin complexes, the orbitals are filled first with 1 electron each and then afterwards pairing take place, while in low spin complexes the T2g orbital is filled first, then pairing take place in that orbital and then the orbital enters the Eg orbital. This is because in low spin complexes the delta O value is more, while in high spin complexes the delta O value is less, the separation is less, so pairing take place, while in low spin complexes separation is more, so pairing do not take place. So let's see the next topic, that is factors affecting the CFT parameters, that is delta O. Now delta O is it is affected by the strength of the ligand. So more strong the ligand, more is the splitting, that is delta O value will be more. So cyanide will cause more splitting than iodide. We have seen in the series that iodide is a weak field ligand while cyanide is a strong field ligand. Now the next factor is the oxidation state of the metal. Higher the oxidation state of the metal, more is the splitting. So Fe3 plus will cause more splitting than Fe2 plus. So with this we come to the end of this lecture. Thank you.